Okay, so now we have a culmination of all the results that we have been looking forward to in our previous several sections. We're going to show how to use the extended echelon form to find the null space, row space, column space, and left null space of a matrix all at once. Okay, so let's make the statement. So back up and make sure we have all our conditions correct. Suppose A is any matrix, n by n matrix, and suppose the extended echelon form is n. Suppose the reduced row echelon form of A has r non-zero rows. Then C is the submatrix of n formed from the first r rows and the first n columns, and L is the submatrix of n formed the last m columns and last m minus r rows. Now what's he saying here? He's just saying that if you have A, you have A and I, and this reduces to B and J, and we break B up into the 0 rows and non-zero rows, and you're taking C0 here, and then you have L down here. I forget what letter this was. I think it was M, something like that. So to find these null space, row space, column space, left null space, you're going to focus on these two submatrices. From the last section, we discovered that both of these are in reduced row echelon form. In fact, C is the reduced row echelon form of A without the 0 vectors. And L is the reduced row echelon form that enables us to find the null space of A. Okay. So let's go through these conclusions. First of all, null space of A is the null space of C. Now that follows almost immediately, because when you row reduce A, you get C and 0 on the bottom. Now the zeros don't add anything. We know that the null space is going so the null space of A is just going to be whatever makes whatever null space you get for C. All right, second one, row space of A is the row space of C. Well, we know that when you do row operations, you don't change the span. And these 0 vectors, again, they don't span anything. So these row vectors of C will span the same as the row vectors of A. The column space of, all right, third one. The column space of A is the null space of L. Okay? That was what we did in the first part of this section when we looked at four subsets. Go down a little bit. That was this thing, computing column spaces. We computed column spaces exactly by taking this matrix, row reducing, taking this part, which was L, and then finding the homogeneous solution. Okay, so we've knocked down the third one. The fourth one says the left null space of A, which is the same thing as the null space of A transpose, is the row space of L. Okay. So these first three can follow pretty quickly. This fourth one is somewhat involved. The proof takes a couple of pages, and I don't really think it's worth proving. It's nice to have a complete set of equations here, but for our purposes, since the left null space is not very useful, I'm not going to bother going through this proof. You can read the proof here. Most of this proof is that last one. From here down to, see, it's a little bit long. Down to here is the proof of the fourth part. Okay, so I don't think it's worth going through this just for that result that we won't be using very much. Okay, so let's look a little more carefully at what we've proved. So look at the situation when R equals M. Okay, in this case, the number of non-zero rows of the matrix is equal to the number of rows. So when you do this form here, when you take AI and you do this row reduction, which is Bj, and remember, we have no 0 rows, so we have C here, and we don't have any matrix L at all. We only have matrix M. Now, the conclusion here was that the the column space of A is the null space of L. But L doesn't exist. Okay? So what does that mean? That means that anything goes. That means that the columns of A will span any vector. Okay? So that's the special case here. We saw that in the case of an n by n matrix that's non-singular. If you take an n by n matrix that's non-singular, then this is exactly what you get. In fact, you have B as a non-singular matrix. B will be the identity matrix. J is the inverse matrix. L doesn't exist, and in fact, the column space is all possible vectors. Okay, so that's what happens when you have R equal to M. Okay, so let's apply this theorem for some particular example. Take this matrix A. When you do the row reduction, you're going to add on when you do the extended row echelon form, you're going to add on a 4 by 4 matrix. Okay. When you actually do the row reduction, you'll end up with a 3 by 6, and here you have a 1 by 4. All right, so to get the null space of A, we just find the null space of C, which we can solve in the usual way. Remember how you do that? You have the 3 variables. For each free variable, you're going to have one vector. To find the row space of A, we find the row space of C, which is just the rows, and here they're written as columns. Notice this first column is the first row, second column is second row, and so on. The column space of A is the null space of L. Here is L right here. Now this is actually in reduced row echelon form. We have 1, 2, 3 free variables. Okay, if we work out the solution in terms of those 3 variables, you're going to get these 3 vectors, and the null space is this space that's spanned by these 3 vectors. Okay. And the left null space of A turns out to be this vector itself. All right. So you can do the same thing with the second example. Same procedure. Look at these examples to firm down the concepts in your mind. And there's more background information here and more ways to look at this situation. But I invite you to read that. But we've covered enough to know how to do the computation, so I'm going to stop here and give you a chance to work on things and gain understanding by working with matrices.